Hi Mark, the number 5 on your worksheet is a hugely difficult problem. It's pretty advanced. Not sure why it's in your first year chemistry class. The lattice energy calculation from the given data here is known as the Born-Haber cycle. Born for Max Born, Nobel Prize winner. Haber for Fritz Haber, also Nobel Prize winner from a couple centuries ago. Let me help you to understand all the data here first, and then I'll help you to understand how to approach this problem. The enthalpy of vaporization here is, let me get a new page for you. The enthalpy of vaporization here is the energy that it takes to change 1 mole of aluminum atoms that are in a solid, kind of like aluminum foil or something, into a mole of aluminum atoms in a gas. So it's the energy it takes to vaporize a whole bunch of aluminum atoms. What about the dissociation of oxygen? The energy that it takes to separate a whole bunch of oxygen molecules, O2, into free oxygen atoms, 2 oxygen atoms for every molecule of O2. So in other words, you have to break this bond. Excuse me. This is the O, this is the O. This bond, you need to break that bond. This is the energy that it costs to break a mole of those bonds. Oops. And the first electron affinity of aluminum, that is the energy that it takes, or the energy that you get when you force aluminum to take 1 extra electron, making aluminum minus the ion, right? That's the energy that you get when you try to do that. You know that it's an energy that you get rather than an energy that you put in because of this negative sign. Okay? The first electron affinity of oxygen, that is the energy that you get when you try to add 1 more electron to an oxygen atom, not molecule, atom. You get the O minus ion, and you get this energy. Second electron affinity of oxygen, when you have the O minus ion and you add 1 more electron, that is a second extra electron, because O minus is an O with already 1 extra electron on. To get 2 minus, 2 extra electrons on the O, that costs you energy, and this is how much energy it costs you, 844 kilojoules for every mole that you try. Right now, heat of formation of aluminum oxide. Now this is a special, this is a chemical equation that's part of a special definition of heat of formation. The heat of formation is the energy that you get, or the energy that it takes, when you try to form exactly 1 mole of this substance. In this case, it's the heat of formation of aluminum oxide. So it's the energy for making 1 mole of it, right? So you have to have, here's aluminum oxide, which we found previously. It has to be just 1 mole. It can never be 2 or anything else. And you'll see why that's significant. When I try to balance this equation, notice that I have to have a fractional coefficient here. This has to be a fraction. And many chemistry teachers have their students get rid of all the fractional coefficients by multiplying the entire equation by 2, so it will be 4Al plus 3O2 makes Al2O3. Makes 2 Al2O3s, but you can't do that for heat of formation, and the reason is the heat of formation is specifically for the energy that it takes, or that you get, for making 1 mole of this thing, and only this thing, just 1 mole of it. So there's no putting 2 here. It's not allowed. All right, now, why does this have to be O2? It's because also in the definition of heat of formation, you need to make this compound out of the pure elements in their standard states at room temperature. So aluminum is a solid at room temperature. That's its standard state at room temperature. Oxygen is a gas at room temperature, and it's a diatomic gas, meaning it always exists as O2 at room temperature, never as O, just floating around, never like this, always like this. Okay? So because of those special features of the definition of heat of formation, the equation has to look like this, right? So there you have it. And the negative sign on the delta H means that you get this much energy when you do 1 mole of this reaction. So there's some more data that's required here, and that data is, those data are the ionization energies. Now, I don't have access to the table that your teacher linked here, so I just got the ionization energies from a different website, Oregon State University, but these are probably very close to the ionization energies that your teacher gave. Okay, so I will list these in purple. So the first ionization energy, I'll put E for energy, for Al, that is the energy that it takes to grab 1 electron from Al. So to take Al and to get Al plus, that's Al missing 1 electron, and 1 electron. So in this chemical equation, I've grabbed 1 electron out of Al to get Al plus and 1 electron. Those are the products. All right, and the energy there is 578 kilojoules per mole. We'll do that in green. So that's 578 kilojoules per mole. Okay, and then also relevant is the second ionization energy. Second ionization energy for Al, and that's going to be, you take the Al1 plus ion and you grab another electron, the second electron, so you get Al2 plus. Oops. So this here is the second electron, okay, from aluminum, and that costs you 1820 kilojoules per mole. Alright, now the third ionization energy is going to be 2750 kilojoules per mole, but the third ionization energy that is the third electron. So you take the Al2 plus ion, which we had after we did the second ionization energy, and you take another electron off, you get Al3 plus. And the energy to do that was, what was it again? Sorry, 2750. Okay, 2750 kilojoules per mole. Okay, so these are the energies that we'll need. These are the data that we'll need. There is an extraneous piece of data that we won't need, and that's this one. You remember from the previous problems 1 through 4 that the Al atom forms a 3 plus ion, right, Marc? 3 plus ion? It's never the 1 minus. Never ever. Come on. This is ridiculous right here. This is just a red herring to throw you off. Well, anyways, we'll use all the data except for that one. Okay. Now this is a hard problem, Marc. So the complexity is going to be pretty high here. I was trying to get a new page for you. Yes, it didn't work. Oh, there it is. There's my new page. Okay. So here we go. Now in this problem, you're looking for this the energy that it takes to bring this ion together with this ion to make this compound in a crystal form. Okay? That's the lattice energy. The lattice energy is, let me balance this out for you, the lattice energy is the energy that it takes to bring ions in the gas phase together to make the crystal. Okay? So that's the, in fact, when you make a crystal, you don't have to put in the energy. You get energy from that because making bonds releases energy. So the crystal, the lattice energy is just the energy of the crystal, the energy that you get when you bring these ions together from the gas phase. just free-floating ions in space together into a crystal. It's really a theoretical kind of energy. It's very hard, or in some cases impossible, to measure the lattice energy purely just by itself, just the lattice energy. But it's a useful number to have, just in order to understand crystal structure and that sort of thing. So the way people calculate lattice energy is by adding and subtracting the energies of other reactions that are related to this, and that's what we're going to do. So there is a law in chemistry. It's called Hess Law. I think you might learn of it later. In Hess Law, Hess Law says that if you know the energy that a chemical reaction requires, or the energy that a chemical reaction produces, you can add that chemical reaction to other chemical reactions, and you can add up all of the energies of those chemical reactions and get the energy for the total reaction of all of them. Okay, so it's like if you added the energy for you, Mark, going to the kitchen, opening the refrigerator, and taking out something cold. Right? There's the energy of you getting up, there's the energy of you going to the refrigerator, and there's the energy of you opening the door, and there's the energy of you taking something out, and there's energy of you closing the door. In each of those steps, you use energy. If you add up all those steps, the total reaction there is Mark took something out of the refrigerator. If you add up all of the energies, the total energy is the energy that it takes for Mark to get up and take something out of the refrigerator. That's what Hess Law is, and that's what we're about to do. So we have the energy that it takes to bring aluminum from solid into gas. We have that, all right? It's right there. There it is. We have that, okay? And we have the energy that it takes to get aluminum, which is a gas, into aluminum plus and 1 electron. We have that, okay? It's right there. It's right here. There it is, right there. We have that, okay? Now, I need some more room here, so I will move this down to the bottom. Okay, so we have that, okay? Now, we have also the energy that it takes to take aluminum plus into Al2 plus and another electron. We have that energy. See? It's right there. That's the energy. And when I say that's the energy, I mean this part. This is the energy, of course, right? These things in green. And we know the energy that it takes to get to take aluminum 2 plus and make aluminum 3 plus finally, and another electron. We have that. Where is it? There it is. There's the reaction, and there's the energy. We have that, okay? So all these reactions up here get us, so just do that in another color, probably do that in marigold. Okay. These get us the aluminum 3 plus ion. Do you see that, Mark? This aluminum 3 plus ion, it comes from aluminum, but at room temperature, aluminum is a solid. So, I mean, just ordinarily, in other words, ordinarily aluminum is a solid. So if I want to make aluminum oxide, the crystal, I'm going to take aluminum, which is ordinarily a solid, and turn it into aluminum 3 plus ion. And in order to do that, I got to go through these 4 reactions, for which we have all of the energies, as shown on the other page. Okay? So now, stay with me now. This is very hard. Okay, now, I'll use a different color, maybe just blue. All right. So now, what about the oxygen? Let's see. What about this oxygen ion? Okay. It's usually called the oxide ion, but that's not important. Right, so to get the oxide ion, I got to turn this oxygen gas, this oxygen O2 molecule into atoms first. All right, so I got to turn this O2 into oxygen atoms, and we have that energy. There it is. This is the energy, right? And then to get the oxide ion, I got to take each of those each of those oxygen atoms, right? Each one of those, and turn that into an ion by putting an electron on it. So I put an electron on it, and I get O minus the ion. And we have that reaction, and we have that energy. There it is, and there is its energy. But this lattice energy is about the O2 minus ion, not the O minus ion. So I need to take that O minus ion and give it another electron. I got O2 minus now. That's what I want. So all these three reactions, they give us the O2 minus ion, which we need for the lattice energy. Okay, and I have that reaction and that energy right there. Okay. So now here we have all the energies, all the reactions, and all the energies necessary to make this and to make this to ultimately make the aluminum oxide compound. Okay. So there is a problem though. We have this energy, 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 but we don't have this energy. This reaction is the energy for this reaction is the lattice energy. And this is what we don't have. This is what we don't know. So how can we find this? We'll find it by subtraction. Why? Because if we add up all of the energies on the page that you see here, including the lattice energy, which we don't have, but just excuse that for a moment. If we add up all those, we will get the following. Back to black. We will get aluminum, or two aluminums, plus two aluminum solid plus, that's an S, plus 3 halves O2 makes Al2O3. Okay, so we will, if we add up all of these reactions, we're supposed to get this reaction, and I'll show you exactly how we get that. Okay, it's just like algebra. So we'll get aluminum solid and 3 halves oxygen gas, making aluminum oxide. We know the energy for this reaction. That energy is right here. Here it is. There it is. We get this is the energy for that reaction. And so we know this energy. Here, let me just in fact write them down. 1669.8. Okay, these are all in kilojoules per mole, right? 1669.8. We know that. This we don't know. We don't know the energy for this. I'll call it X. We know the energy for this. That's 844. 844. We know the energy for this. That's negative 142. We know the energy for this dissociation. That's 496. We know the energy for this. That's aluminum. That's 2750. You see what I'm doing, right? We know the energy for this, 1820. Just notice what I'm doing operationally right now, just like at a very menial level, and then the conceptual part I'll bring in a very short moment. Okay, and you know what I'm doing with this for the vaporization. We have that energy 284. Okay, so look, Mark. Here's the conceptual part. You add up all of these energies, that, and X, including X, right? All of that plus X equals negative 1669.8. What does that look like to you? Whole bunch of stuff plus X equals a number. So that's just algebra. I can just subtract all this stuff on both sides of the equation to get X. Okay. Let me show you exactly what I mean, because I don't know if you are following or not, because you're not with me right now. So this number is all this stuff added up, okay? All this stuff added up plus X equals negative 1669.8. Okay, these are sixes, sorry. Right, so that means I can just subtract this number on both sides. So X equals negative 1669.8 minus that big number, which is known to us. All we've got to do is use a calculator, okay? And then we'll get it, okay? So that X, remember, is the energy for this reaction down here, and this reaction is the lattice energy reaction, because by definition, lattice energy is the energy that you get when you bring ions together to form a crystalline solid. bringing ions together, that means the ions are freely floating in space as though they were gases. Although in nature it's very hard to get an ion into to become a gas, but this is the chemical equation for lattice energy. So that means the energy for this chemical equation, which is X, is the lattice energy. So that's what we want. Okay. Now I'm going to show you how to add up all of these reactions in order to make this true, in order to get this reaction down here. In other words, I'm going to show you how to make this equation true. Right? This equation here. I mean, this X equals blah blah. How can I validate that? How can I make sure it is true? Now, this is also algebra. Okay. So here we have some chemical equations, and they all have arrows in them. There are things on the left of the arrow, which are the reactants, and things on the right of the arrow, which are products. Okay? We're going to have to make a few changes to these things, but all the changes that we make are going to be legal in math. What I mean by that is if we multiply some chemical equation by 2, we're going to multiply everything in that chemical equation by 2, the reactants and the products. You remember in algebra, like in in algebra 2 when you do linear combinations, like you have 2 equations, 2 unknowns, and you add those equations together, or you change the sign of one of the equations and you add them together, or you solve for both x and y. Okay. This is exactly the same thing. All right, so here we go. Now I have aluminum here as a gas and aluminum here as a gas. So the fact that I have aluminum on the right of the arrow and aluminum on the left of the arrow, the fact that both of those appear means that I can cancel them out. Okay. Okay. So, but before I start going canceling things out, let me make sure that I have enough aluminums. All right. So at the end of the day here, I need 2 aluminums. The total equation says I need 2 aluminums. So let me make sure I have 2 aluminum solids. I only have 1. So I got to multiply this by 2, this by 2, and therefore I have to multiply this by 2. Okay? And if I have aluminum gas here, there is no aluminum gas in the total equation. There's aluminum solid, but no aluminum gas. So I don't want to have aluminum gas showing up in the total, so that means I have to cancel this out somehow. How can I do that? I can cancel the product aluminum gas with the reactant aluminum gas, but there's only 1 here, whereas there's 2 aluminum gases up there. So I got to put a 2 here also. 2, 2, 2, 2. So great. Now I can cancel. I'll use brown to cancel. Bang, bang. Oops, bang. They're gone. Okay? Back to green. Now, here is aluminum 1 plus ion, and here's also aluminum 1 plus ion. Is there aluminum 1 plus ion in the total equation? There is no aluminum 1 plus ion in the total equation. I need to cancel that out. Aluminum 1 plus ion the product, aluminum 1 plus ion the reactant. They can cancel, but this has to be 2, because there are 2 there. 2, 2, 2. Everybody's 2. Goodbye, aluminum 1 plus ion. Goodbye. Goodbye. Now I have aluminum 2 plus ion. Is there aluminum 2 plus ion in the total reaction? No, there isn't. That needs to leave. All right? So that means I need to get aluminum 2 plus here, aluminum 2 plus here, aluminum 2 plus. I mean, and everything has to be multiplied by 2. Sorry. In the product, that's actually a 3 there. That's aluminum 3 plus, not 2 plus. But everything does have to get multiplied by 2. Right? So there it is. Cancel, cancel. It's gone. Now I have aluminum 3 plus ion. Is there aluminum 3 plus ion in the total equation? No, there isn't. I need to get rid of it somehow. Where can I get rid of it? Oh, look, right here. There's aluminum 3 plus ion, and there are 2 of them as a reactant. So the 2 aluminum 3 plus ions in the products can cancel. How convenient. What about oxygen? Is there oxygen gas in the total equation? Yes, there is. Oxygen gas is right there, O2. But there are 3 halves of them. That means I have to have 3 halves in the among the summed up reactions up here. So 3 halves, multiply everything by 3 halves. Multiply that by 3 halves. Multiply that by 3 halves. Everything. Okay? Just like algebra 2. Alright, so here we go. So now I have 3 halves times 2 is Just 3, right? Because the 2's cancel. Blip, blip. So I just have 3. Now I have 3 O's here. Are there any O's in the total equation? Just O alones? Well, there's O2, but that's not O. There's O3, but that's not O. Are there any lone O's? No, there aren't. That means I have to cancel this lone O. So I got 3 lone O's. How can I get rid of them? Well, there are some lone O's. There's a lone O as a reactant here, so I need 3 of these. 3, 3, 3. So now I can cancel these 3 lone O's, whammo, with these 3 lone O's, whammo. So now I've got 3 O minuses. Are there any O minuses in the total equation? No, there aren't. They need to leave. All right, so 3 O minuses, 3, 3. Then I can cancel these product O minuses with the reactant O minuses. Now I've got 3 O2 minuses. Are there any O2 minuses here? There aren't. Those need to leave. Are there any O2 minuses elsewhere in these summed up reactions? Yes, they are. There are, right here. See? O2 minus. Look, there are 3 of them. Ha ha! And they're reactants because they're to the left of the arrow. So I can cancel the product O2 minuses with the reactant O2 minuses. Now, what else have I got in here? I've got electrons. Are there electrons in the total equation? No, there aren't. I need to get rid of these electrons. How many electrons have I got? I've got 3 electrons in one equation and 3 electrons in the other equation. That's 6 electrons. Those are reactants or products. They're to the left of the arrows. That means they're reactants. I need to find 6 electrons to cancel with among the products. Oh, look. This is convenient. 6 electrons as products. Cancel, cancel. Okay. The only survivors in the above summed up reactions need to be everything that you see in the total reaction. If there's any other survivor, you've done something wrong. So let's see. Okay, let me use yellow. Right? 2 aluminum solid. 2 aluminum. 2. Trying to get this mark. Okay. 2 aluminum solid. That is a survivor. Who else is surviving? Who else? I don't see any other survivors. That's odd. Aha! 3 halves oxygen gas. 3 halves O2. That is a survivor. Are there any other survivors? Everybody is annihilated. Oh, there's one more survivor. Al2O3 as a product. That's a survivor. Okay, so the only surviving product is Al2O3. There it is. Al2O3. Check. The only surviving reactants are 2 Als. Whoops, where's my... Oh, here it is. 2 Als and 3 halves O2s. Confirm. 2 Als, confirmed. 3 halves O2s, confirmed. Okay, that means everything is correct. So we can now solve for x. Okay? Here's how I solve for x. Calculator. Calculator. Okay, here it is. Here's the calculator. Okay, this is what we do. All right, here we go. 2 times 284 plus 2 times 578 plus 2 times 1820 plus 2 times 2750 plus 3 halves is 1.5, as you know. 3 halves times 496 minus, because negative 142, right? Minus 3 times 142 plus 844 equals 12026. All right. So going to that other page, this stuff right here, this stuff wasn't really stuff. It was 12026. Silly Glenn. It was pen. Okay, 12026 plus x equals negative 1669.8. That means x equals negative 1669.8 minus select tool, delete, pen. 12026. Okay, this is good. So x equals calculator 12026. Okay, you're good at math, so I don't really need to do this whole thing. But anyways, 13696. So this should be about negative 13. It should be something like this, you know. And of course the units. What are the units? Well, let's see. I didn't put any units here. Where did I put the units? Where are those silly units? Where are they? Hello, units. Okay, here they are. They are all in kilojoules per mole. See that? Kilojoules per mole? Everybody's in kilojoules per mole? Okay, so that means the units are kilojoules per mole. Kilojoules per mole. Okay, so that's supposed to be the lattice energy. You see that's negative? That means that when you bring ions together to form a crystal, a huge energy release occurs. And that kind of makes sense, because that means that crystals, the aluminum oxide crystal anyway, is lower in energy than aluminum and oxide ions just by themselves. And does that make sense? Yes, it does, because when you go outside and put a piece of aluminum on the ground, it will soon turn white, just gradually, because aluminum oxide forms on that aluminum foil. In fact, aluminum foil is always covered with a very fine layer of aluminum oxide. But anyways, aluminum oxide is obviously solid. I mean, anything that coats without really coming off, unless you scratch very, 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 very hard, is a solid. So since aluminum oxide, you know, from everyday life is solid, it must be a pretty low energy material, because high energy materials tend to be reactive, and they tend to come off if you just throw water on it or expose it to air or something. But low energy materials, you have a lot of. Water, for example. Water is a low energy material. Carbon dioxide. Carbon dioxide is a very low energy material. That's why those two things are very, very common. Well, anyways, that's besides the point. Let's check this answer. Lattice energies are widely studied by material scientists trying to create new materials. So let's see. Lattice energy, aluminum oxide. If the published lattice energy is similar or close to ours, we should be able to, then we'll know that we've done something right. Let's see. Lattice energy of aluminum oxide, lattice energy. Okay, so someone on this Doc Brown page found 15916 kilojoules per mole. So let's see. Is that close to ours at all? 15916. Yes, it's quite close. It's off by 2000 kilojoules or so, but that's okay. I was really looking for the order of magnitude. If it were found that if other people had found this quantity, then there would be some worry there, because that means we would be 10,000 off. But since we're only a couple thousand off, I think that might be okay. Let's see. Is there another person who has published their lattice energy for aluminum? Something maybe .edu, which would be more reliable than .info. Let's see. Here we are. Ooh, webelements.com is pretty reliable. And they also calculate lattice energy of 15916 kilojoules per mole. So, okay, this website is taking long to load. Okay, here we go. So, where are the oxides? Okay, so the lattice energy is 15916 kilojoules per mole. So that tells me there might be something wrong with my calculations here. What might that be? What could be wrong with what I've done? There's nothing wrong with this number, so there must be something wrong with this number. This number is too small. What did I miss? Did I miss something there, Mark? Okay, so the fact that two sources both said 15916, that suggests to me that it really is 15916, and since our calculation here was theoretical, ours should be pretty accurate. But then again, 15916, that might be an experimentally derived number. So there's always an inherent error in any experiment. But still, I'm a little concerned. So let's redo this calculation. Well, I have a better idea. If you understand this because of my explanation here, would you redo this calculation, please, Mark, and then let me know what you get? You should get 5916, I believe. I must have done something wrong here, maybe mistyped something. Would you redo the calculation, please, and then let me know if I've done something wrong? You can just send me email, if you're busy. And I know that you are busy this weekend, okay? Thank you. Also let me know if this was helpful at all. Also, let me know if the other videos were helpful. In my opinion, the other videos, I kind of predict that they wouldn't be as helpful to you because musicians tend to be good at technical stuff such as math. And chemistry is a technical thing such as math. So I get the same number. I'm actually doing something wrong. So I don't know. I think you might not have found the other video, but I would like to know from you which videos were helpful, which were not. Thank you. And please redo this calculation and let me know if you get anything closer to 15916 kilojoules per mole. Thank you.